3 o'clock. I gotta say, this is the most people I've ever had at a conference for crypto talk. And it's not the first one in the morning either, so I appreciate the BSides folks. This talk is Tales from the Crypt, a cryptography primer. I'm Adam Englander, and if you want to say great things about my presentation, there's my Twitter handle. So who am I? I'm a senior engineer at Innovation, which is a fraud and security company. I'm an IoT enthusiast. I love building little things and talking with people about how they have terrible security for them. And I am a national junior basketball girls coach for Division I, which is truly my passion. So who I'm not, I am not an official security researcher. I work for a company that is a security company, so I have to understand a lot of this stuff, but it's not my job. I'm not a cryptographer because I don't have a PhD in mathematics. And again, I'm not a mathematician. That said, you don't have to be any of these things to understand how crypto works, and which is what my talk is really for. Because what we're going to discuss is some of the common methods and terms using cryptography, maybe a little more familiar to this crowd, and specifically in application development. And one of the things that I found is I was in fintech for 7 years, and I was using crypto wrong. Because it wasn't really what we did, right? It was something that we had to do, and we were PCI compliant, and we passed all of our specifications, but if somebody ever grabbed a hold of our stuff, they really, really wanted it, they would have had it. Because we were doing some things really, really terribly. And I didn't learn that until I came to a security company, where I had to actually learn how to do encryption, and learn how to properly do digital signatures, and learn what was acceptable, what wasn't acceptable, what's hackable, what's not hackable. So we'll talk a little bit about that. For those of you who don't know, cryptography, according to Wikipedia, is a practice and studied techniques for secure communication in the presence of third parties called adversaries. Fortunately, I don't have to explain adversaries here. Some places you do. What does that actually mean? And what that means is cryptography obscures data in a way that's difficult and costly to duplicate and reverse. There's probably been a couple talks. If not at this one, definitely at some of the other BSides conferences on rainbow tables and the super easy ways to go crack people's passwords. We have it at work, right? We have a little machine that we get a password list, we'll throw it on it just to see where things are because we hate passwords and we're trying to eradicate them. So we like to try and find out just how bad they are and how bad people's passwords are. But we still have to use them. Unfortunately, like the world still has passwords, and the world will have passwords for a while, and we don't want to get into the whole biometrics thing on how dangerous that is. And saving your data, right, against attackers is super, super important. If someone gets a hold of your data, right, your last defense is that they can't actually do anything with it, or they won't be able to do it in your lifetime anyway, which is important. And it brings us to the difference between good cryptography and bad cryptography. So, how many people know what entropy is? Right. Almost half. Good cryptography has a high level entropy. That means that it's very difficult to predict the data as far as kind of recognizing patterns, which is super important. And a lot of what I'm going to talk about today is how you can use the exact same functionality and the same algorithms, and you can get very, very low levels of entropy. And that's not what you want to do. It's not going to protect you. Because entropy is important, because all data has patterns. As researchers, you know, right, that you're going to have certain people are going to have the same amount of usernames, same amount of passwords. You will probably know that up until, I believe, 8 years ago, the middle digit of your social security number was where you got your social security card. And so there are pieces that are going to be more than a social security number that are going to be more prevalent. The first number, a particular first number is going to be more prevalent. On a birth date, a particular number is going to be more prevalent. There's going to be more ones, 31-day months that are going to be in there. So there's certain patterns that show up in data, as far as people's names, letters that are used, things like that. And even just in kind of arbitrary data, if you do enough research and you see enough data, you can recognize patterns. Right? We build all these systems to go recognize patterns, and they do them really, really well, and that can be used against you on your data. So it's super important that when you encrypt data or you're creating key derivations, that they don't have recognizable patterns. So this is from Wikipedia. We have this in my office. So this is Tux, and this is an encrypted version of Tux. Right? 7 years ago, that was considered secure. Right? You can absolutely tell that is Tux. That is a terrible level of entropy. Right? There are patterns that are distinguishable. Because I can guess by looking at it that everything, you can tell what pieces are the same color. That's not what you want. So how do you increase entropy, right? And that's a big one. And the way to do it is you mix in, it's a very long thing to say, cryptographically secure pseudo-random data. And that's another point. And when you do that in most cryptography in the form of an initialization vector for block ciphers, or you use it as a salt. So if you're doing key generation or password hashing, as most people call it. And you also increase entropy with feedback loops. So an example of a feedback loop is cipher blockchain. So what you can see here is the reason you're creating entropy is you're starting off with an initialization vector. So the reason that you have an initialization vector for two reasons. One is because you have to start somewhere, right? The algorithm has a way to act. If it doesn't have data, it's not going to work. The other reason for it is that if you do it correctly, that initialization vector is random data, cryptographically secure pseudo-random data. So that even if you have the same value that you're encrypting, it is different every time you encrypt it. So what it does, it takes your plain text, your initialization vector, it does an XOR for that, and uses that with the key and the encryption cipher, and it comes out with ciphertext. Then it takes the resulting ciphertext, and that is your next initialization vector. And it performs the same thing over and over and over and over. And what that does is it ensures that it all looks different. The reason that this looks so bad is because it doesn't actually do a feedback loop. It just uses that same functionality to encrypt the same thing every time with the same key. So every white comes out the same. Every black comes out the same. Every yellow comes out the same. So when you use cipher block chaining, you get that, right? There is no way you could ever possibly know that was Tux. And unfortunately, most libraries, that is not the default. If you're doing software development, what is the default? Is it? So one of the things that I try and do is I try and go around and tell people, here's what not to do when you're developing using cryptography, because the languages don't tell you in their documentation. And I was doing that's called an electronic cookbook. That's a bad example, and I was doing that for a long time. And it's very, very bad. And I was also using static keys, because I didn't understand entropy, and that was very bad. And there's localized versus global entropy. So when you're using a feedback, a cipher feedback, what you're doing there is you are creating local entropy, so that each block, even if the value is the same, the encrypted value comes out different. But there's global entropy as well, making sure that if you encrypt the same data twice, it comes out with two different values. If you have the same password and you key derivate it, you stretch the key and you hash that twice, it's different. Because as we all know, right, top 10 passwords, we could find, if we could go into a password database and go find, oh, this same hash value shows up in here 3,000 times, that's one of the top 100, so I'm just going to brute force that and I'll get it, it knows that well. If every one of those is completely different, then that's a much more difficult case. So cryptography types, there's basically two types. There's symmetric key cryptography, which is where you have a secret that you share, or it's just you reading your own encryption. or asymmetric key cryptography, which is private-public key pairs. And then there's cryptography applications, and there's some other cryptography applications, but the ones I'm really going to talk about are going to be kind of common day-to-day stuff, which is encryption, digital signatures, and key derivation. So encryption is protecting data that needs to be recalled. And to me, that's a very important distinction. Until I started working at Innovation, which was actually at that time LaunchKey, I had never thought that if I don't need to actually recall the value, then I can just hash it. And then it's a little more secure. Like even I don't know what the value is, which makes it a little more secure, at least internally. And one of the places that we do that is emails, telephone numbers. We don't email people, so we're fairly safe on our side. But we do need the email too if you need to wake another device. There's things that you need to do that you need to provide the email. Well, if you provide it to us and it matches the hash, that's fine. Now we know the email we sent off, but we don't store it. And I would say, at least consider something like that. If you don't need to know what the data is, the best way to keep it secret is just not knowing what it is, not being able to reverse it. But encryption allows it to be reversed, and it's reverse speed encryption. Digital signatures are used to verify the authenticity of the data. How useful that is in certain situations is very different. You probably downloaded something and said, use this SHA to make sure that it's the same, but you got it from the same website you download from. So if one's Chrome, the other one's probably Chrome too. But that's basically what it's doing, is it's verifying the authenticity. And in cryptography, it gets a little more than just a SHA, where you're doing HMAX using a secret where you can verify that. They cannot be reversed, but they can be reproduced for verification. And then there's key derivation, and most people call this password hashing. And I try not to say password hashing very often unless people look very confused, because that means people think that they can use SHA-1, SHA-256, and MD5 for password hashing. It is scary to me how many people use standard hashes for passwords. If everyone remembers the, I'm trying to remember that crazy cheating site that got hacked 2 years ago. Ashley Madison, right? So Ashley Madison, they did their passwords right. They used bcrypt on the passwords, but they created this thing for the website, for the API, that actually used a SHA-256 of the username, delimiter, and the password in plain text. That's how they got everybody's passwords when they got hacked. It just kind of blows my mind sometimes. So I try and just keep people from actually thinking about password hashing. It's key derivation. And it cannot be reversed, and it is computationally expensive by design. You can, if you have a SHA-256 password, I believe using, 10 EC2 instances, you can break it in like 7 minutes, right? A giant list. So where key derivation changes that is it just iterates over and over and over and over and over again, taking up as much time as, depending on the function, taking up as much time, as much memory as it can to make it just really hard for you to just brute force it, which is pretty awesome. So on the symmetric key side, I'm going to talk a little about what's kind of different between symmetric key and asymmetric key. And there's advantages and disadvantages to both. And a lot of the times, we actually use both at the same time. And I'll kind of talk a little bit to that. So, symmetric key cryptography uses shared secrets, which is super easy, but it's a shared secret, right? You're giving out the keys to the kingdom to someone, which is inherently sketchy. You have to have a whole lot of trust that they're not going to, I mean, you can be as secure as you want, but if you hand that secret to somebody else, then how secure are they? A lot of times it's okay internally, it's up to you to decide what's okay for you, but that is the problem with a shared secret, is it's shared. It uses cipher algorithms against blocks or streams, and most implementations use a block. Even if you're doing streaming, you're probably streaming chunks, and you're probably encrypting those chunks. And the reason for that is that stream ciphers use almost no resources, so they're not actually doing difficult functions, so they're very easy to crack. So you don't see a lot of stream ciphers out there anymore, because they inherently make things less secure. we're talking about blockchaining, we'll talk about block nodes. Do not use electronic notebook. Do not use electronic notebook. Do not use electronic notebook. It sounds really cool. ECB sounds just like CBC. They all have the same like sounding vowels, which is awesome. But do not use ECB. That's the one that had tux that you can see. Because it does not have a cipher feedback mode. Again, do not use ECB. So cipher blockchaining, the entire message is required for decryption. So you'll find that most implementations are probably a really good candidate for CBC because it is supported everywhere. There's some newer stuff out there that I'm really not going to talk about with elliptical curves and all this kind of nice stuff that may or may not be supported by your library. But cipher blockchaining is basically supported everywhere. And because it has a feedback mode, its particular feedback mode, the entire message is required. If you're missing a piece, you get nothing. Which is the beauty of it, is that you have to be able to decrypt the whole message. You can't just, you can't get to the end without the beginning or the middle or anything in between. And the full ciphertext block is used to seed the next block, which is differentiators. So there's some different feedback modes, and those are differentiated by at what layer they're actually creating feedback. Because sometimes you don't want it to actually be the whole message. So we saw this already, and I kind of went through it, where it basically take your initialization vector, builds a ciphertext, feeds that back in as the next initialization vector with the plain text, and goes again. So every part of the first block is needed for the second part, to create the second block. So next one is cipher feedback, and it's considered a self-synchronizing stream. So if you miss part of the data, you can pick it up again. And the reason for that is in the feedback mode. So in this feedback mode, what you see is that you take the plain text and it goes into the encryption. The initialization vector is used at the beginning, and it XORs your plain text with the encrypted vector. So you don't need because of this, you can actually start again once you miss a piece, right? So you're still getting your entropy because they're changing as they go along to the feedback mode, but you don't need the first message to be able to decrypt the last message. So if you're doing video streaming and you're encrypting that, or if you're streaming large amounts of data, this is probably something that will be more attuned to that, because if you lose a packet, you don't lose the whole thing. If you're transferring large pieces of data, you probably want the whole thing and you want it accurate. But if you need to be able to have something where you can have a disconnect for a while but keep going, cipher feedback mode might be more to your liking. And then there's output feedback mode, and this differentiator is the entire message is needed for decryption. The full ciphertext block is used as the seed for the next block, which is not correct on that one. That's a bad slide. So on this one, what you see is you've got basically the same thing, is that you are encrypting the previous block. So you've got the result of the previous block, the initialization vector, and encrypts that, and then moves to the next one, and does the key there. So it's actually the encrypted IV that's being used for the XOR instead of the entire packet. So its disadvantages is that, well, there is one advantage, that you can actually pre-generate your encryption. So if you're going to be streaming out data and you're concerned about latency, you can actually regen the entire piece and then XOR it with your actual plain text and then ship it out. So it is inherently less secure because of that. But again, there are some you have to decide what's more important. Is the ability for speed or resumption more important than the ability to, or the level of encryption? But this tends to be used when, like I said, you need zero latency on your encryption, and you want to make sure that you can, so you just basically pre-generate your encryption stream, XOR it as it's going out, and you've got the encrypted value. Which also means that you can pre-generate the other side too, which is as long as you know the initialization vector, you can start building it before you start receiving data. Any questions about any of those? I go through them really quickly.
the difference between this one and the last one? It looks the same to me.
So the big difference here is that this one, you're only encrypting your initialization vector and then the encrypted initialization vector. It does not touch the plain text at all. So you're never encrypting your text.
See the other one?
The other one, it's after you get the encrypted text, but it doesn't actually use the full ciphertext as feedback. So you can start over, you can start from here and go ahead, but you're actually encrypting the data. But it's at a point where you can recreate it if you pick it up in the middle. There's subtle differences. And this one's just kind of the really odd one where you can just pre-generate your entire piece you're going to do the encryption with and just XOR your data as you're shipping it out, and then it comes out encrypted on the other side, which is really odd. Did that answer your question?
Yeah.
Okay. Any other questions about the feedback modes before we get to digital signatures? Or anything on the encryption side before we get into digital signatures? Everybody's yeah.
So all these codes are used practically in practical applications or only CBC?
Most applications use CBC because unless you have streaming data that you're okay to miss a piece. So if let's say you've got telemetry data coming from a remote satellite or whatever the case may be, water tower, a pump out in the middle of nowhere that's spitting out data that you want encrypted. If you miss a piece of that, whatever, I'll pick it up when I get it back. And then there are specific ones where you need to be able to ship data very quickly, where both sides can pre-generate the encrypted side and then just match it up for encryption and decryption on the other side. So I don't know of a whole lot of places where you'll be using output feedback, but that's basically what it's for. It's for zero latency. Because as we all know, the reason cryptography exists is because it's computationally expensive, right? And so if you can do the computationally expensive stuff and not do that in real time, you can pre-bake your computation and then spit everything else quickly. You can probably do a higher level encryption without creating any latency in your system. So they're used in the real world. I've never seen an actual implementation of this, but I have seen for when you're setting data streams in chunks is where you can use the output feedback. Question?
It's been forever since I've taken hexadecimal math, but you are using XOR, right?
Yes.
Okay.
XOR, yeah.
All right. And I forget what there's ands and ors.
Yeah, there's XAND and XOR. And sure. Yeah, I'm pretty certain that's an XOR.
Yeah.
It's been a long time since I've had to look at diagrams like that too. So yeah, it's doing basically byte comparisons against the binary. And doing binary math. It's awesome. And if you ever want to find out exactly what that does, like the greatest place to ever look for this stuff is where I stole this picture from, is Wikipedia. It's amazing the amount of information. If you want to find out the equations, if you want to be a mathematician, if you want to be a cryptographer, it took me like 6 readings to get through most of them before it actually sunk in what it actually did, because they're that high of a hole. So if you want to get super deep, you can do that. All right, any more questions about cryptography? Cryptography is really the hard stuff. Okay. So digital signatures. In symmetric key cryptography, these are hash-based message authentication codes. It's basically hashing combined with a key. And you should always use, who understands about hashing collisions? Okay, so depending on the size of your data, you will likely need to use a high-level SHA. You can't use an MD5 because there's too many collisions. SHA-1, there's usually too many collisions when it depends. And SHA-256 right now is going to give you fairly reliably uniqueness, because what you don't want to do in a digital signature is you never want to have 2 pieces of data with the same signature, because that defeats the purpose. Which is why you can't use MD5 anymore. And if you're doing it against a fairly large set of data, then because you're taking a 2 meg file and you're turning it into 32, 48, 64 bytes, the likelihood of collision gets higher. So the larger your data, the larger you want your hash to be. to avoid collisions, so that somebody can't find a way to adjust your data very quickly and then impersonate it if they figure out your key. Because again, it's a signature. It can't be undone, but it can be assigned. So they can basically, when you're sending a message and you want to determine authenticity with a signature, you don't want someone to be able to do a man-in-the-middle attack, find out your signature, regenerate some data really quickly to find it and ship it off. And the best way to do that is SHA-256 or better. That makes sense? Pretty cool. All right. So asymmetric key cryptography, it gets even weirder. So RSA is basically common and available and what almost everyone uses for asymmetric key cryptography. It uses very large prime integers. So large it is really hard in the IoT world to generate them or store them. So that's why you find a lot of problems with cryptography in the IoT world. They are very computationally expensive to generate. And encrypting using asymmetric key cryptography is, again, very expensive. But the upside is it uses key pairs to protect the secret. And what that means is you get a public-private key pair. And each one can do certain things. Each one has enough information to do certain things. So a private key can do everything. So it has enough information to encrypt, decrypt, sign, and verify, which are the 4 things you can do with public key encryption that we're talking about at least. The public key doesn't have enough information to do anything except for encrypt and verify a signature. Sounds like voodoo, but it's 100% true, and you can actually go look up go to Wikipedia and look it up. So there's just a piece of data that's missing, but it's enough to verify that the data that was signed with a private key can be verified with a public key, and you can encrypt something that you cannot decrypt with a public key, and only the private key can decrypt it. Crazy word stuff. But that's the amazing magic about public-private keys, which is why they're used everywhere, by the way. So if you've ever done TLS, right, you do that with a public-private key negotiation to use Diffie-Hellman to try and get a common key pair that neither one knows what the other one is until you finally get it. It's never transmitted, and then you do AES encryption. But all of our lives are protected by RSA. If you're doing SSH, you're probably doing it through RSA, right? Public-private key pair. You've got your public key that you register. You put your private key locally. You put the public key on the server unless you log in. It does crypto. So key size and hashing algorithms are super important. Key size is super important for everything. But RSA, if you guys probably know, but so Google recently, basically, if you did not have a certificate with a 2048 key or larger, said you'll get a little warning, and then finally a little red bomb. Your site is not secure because a 1024 key is not secure. You can brute force a 1024 key. 2048 key, you can't brute force today, right? But in a couple years, you'll be able to brute force 2048. The size of, like, you are talking about an integer that is 2K, right? That's a prime, not just integer, a prime number that is 2 kilobytes. That's a very large number. So what we try and do is we try and use 4096 where we can, but try and do that on an Android device, you'll be waiting for 5 minutes, which is unfortunate. So some devices don't support large keys very well, but they'll all do 2048, and if you can't do 2048, you've got to really think about your security protocol because you're going to have problems. 1024 is really helpful. And when you're doing your hashware signatures, SHA-1 for RSA is considered safe because of the way that they do it. But 256 is always going to be better. It's just always going to go to 128. RSA has data limitations. So here's where it gets kind of freaky too. So RSA can only encrypt or sign data up to the length of the key size. It just does one operation, right? It doesn't have blocks. It just has one chunk of data. When you do a signature, it's going to do the hash first if it's too long, and then it signs the hash. But you'll also often find that you use mixed cryptography. So you'll use RSA for your key and your ID to encrypt that and pass those along with symmetric key cryptography. So one of the things that we do at Innovation is for all of our communications is we generate a random key and ID for AES. We encrypt that using RSA, and we ship the whole thing along. Because if you've ever seen how large a one-character encryption is of a 4096 key, it's 4096, right? So it's a very large piece of data for one byte, right? So AES makes that smaller, and the only thing that you have problems running into is with your keys are going to be a little large when you're encrypting those. But that works really, really well, and if someone intercepts your data, if your private key gets compromised, they'll only be able to determine the keys and the IDs for that data. And if they get one key and ID, it's not going to work with the other data. Padding. So most cryptography, padding is just something to add the extra bytes so that you can have an entire block and that you can do the encryption. That's the whole reason for padding, is because when you're doing encryption, you have to have a block the size of your key to the XOR. So it will just, you pad it however you want to do it. You can pad it with an all bytes, use PKA7, all kinds of crazy padding schemes that you can do, but they're basically inconsequential. Not the case in RSA. RSA padding is where it creates entropy. So it does pseudo-random padding to create your entropy. Since you're not providing initialization vectors so that everything gets encrypted just differently every time you do it, it does that with padding. So it generates your entropy using padding. So it's important that you use the right padding. If you're doing RSA, most libraries are going to default to PKCS1 version 1.5. Do not use it. Do not use it. Do not use it. It is not cryptographically secure. What you want is the optimal asymmetric encryption padding, which is OAEP. It's been around for almost a decade, and still nobody uses it. So please, 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 if you want your data to be secure, please use OAEP padding when you're using RSA. Any questions about asymmetric key encryption? No? Okay. Key derivation functions, aka password hashing. So, and I'll say it again, only use key derivation functions. Never use standard hashing functions like MD5 or SHA for passwords. My MacBook could brute force an MD5 in no time. A gigantic database, it could brute force a gigantic database in no time. SHA-1, it'd take it a day or two. And if I had an array, it would take it, if I had some GPUs, it'd take me almost all the time. Just, it's not something that you want to do. You may find it in your organizations, right? When I was acquired, I was aghast to find out that a security company was using a SHA-2 password. And with the explanation, well, it's legacy. And it doesn't matter if it's legacy, it's bad, you should fix it, right? So never, never, never use SHA or MD5. So the reason you want to use key derivation is these inject salt for entropy. It iterates to increase the cost, and some of them create cost via threads in memory, specifically that being Argon 2. And bigger is better. So one of the questions I get asked is like, well, how many times should I iterate? As many as you can. As many as you can do it before your users will just think something's wrong. Right? I believe it's perfectly acceptable to hash a password for half a second. Half a second is a lot of iterations. And that's what you want to do. You want a lot of iterations, right? You want to protect that password. So bigger is always better. Bigger passwords, with the exception of, Bcrypt has, I think it's 42 character password, or 42 character limit. The others do not have limits. One of the things that really just irritates me to no end is when someone says your character must be between 8 and 16 characters. Why? You're creating a hash, and it's always the same size. Why do you care how big my password is? Why? What that tells me is you're not doing it right, because you care about the size of the data, means you're probably encrypting it, and I'm going to get it. So bigger is always better. Allow people to make giant passwords, right? I try to make 64 character random passwords whenever I can, because I'm paranoid. So which key derivation function should you use? So Argon 2i is the hottest thing on the planet. It's been around for a couple of years, which scare people because it's only been around for a couple of years. So it hasn't been gone through the standard vetting process of being around forever. But it is a very, very, very cool product. And the reason that it's so cool is that it uses memory and threads. So what it does is it actually makes sure that the memory that it processes is too large for one register in your CPU. So it goes through the process of making sure that you have to really, really work to deal with this. And it's going to spawn threads so that you can't just put it on a GPU box that doesn't deal with the threads very well, where everything has to execute one thread. So it's it won the password competition 2 years ago, and nothing has unseated it at this point. So I guess it's your decision on which is more important to you. Crypt is definitely preferred for password hashing. I get into arguments with people about this a lot. But because it just allows you to automatically make up for how fast your CPUs can go, it's a little better. Bcrypt is acceptable. It's certainly, with the right number of iterations, it is very, very hard to crack. As we all found out for Ashley Madison, because once they got past the top 100, all the password hackers just gave up. It's like, it's too hard, it's Bcrypt, I don't care. PBKDF2 can be used in a pinch. One of the things that PBKDF2 doesn't do that some of the other ones do is they will store with it their information about how many iterations that it has. So if you want to increase your iterations, you can do that and not have to upgrade everybody until they send their nice password, because the salt and the salt iterations are inside of the actual encrypted, or the hash value. So you don't have to know what it is, you can figure out what it is there. So without having to create 3 database entries or having to come up with that yourself, it just does it for you. It's pretty standard. There's a lot of libraries to handle it. And kind of my pitch is no passwords are best. So if you have an application and you have the opportunity not to write your own password management when you're writing your application, do that. Use an LDAP system that is secure. Use something other than storing your own passwords, because this crowd's probably a little different. Most crowds I talk to, you are not security experts. So being security experts, you probably want as little footprint as you can of data that you have to be. So share the data with different systems that people are managing and monitoring all the time, and not stuck in some MySQL database somewhere that you never even pay attention to, or God forbid a SQLite database. So any questions about key derivation functions? Yeah?
When it comes to length of keys, do you run into export restrictions and things like that?
Well, so the keys there, if you're talking about RSA, you are talking about size restrictions. Yeah. So nothing past 24.8, I believe it is now. Especially if you're just using Java, you have to get the extended, or is it the unlimited strength encryption stuff for that. So yeah, there are export restrictions, but I believe those are only to like Iran, China, and a few others. And there may be people here who know that the legal part of that better than me, but that was a question that I actually brought up about this, and as we were moving into Europe, and they said, no, it's not a problem there, it's just unfriendly nations you can't export the key strings. And they probably don't know. So.
They'll just steal your stuff.
Right. And they can just say, why, no, I'm not from Iran, why no on it, so they're good. Any other questions? No questions at all? What did I get wrong? There's always somebody who tells me there's something wrong. No? Nobody has any questions about my findings? Okay. You guys are an easy crowd. Well, it is ending a little bit early because I expected more questions. This usually gets a lot of questions. So if you think you're like imposing to ask questions, don't feel like you're imposing to ask questions. Okay. So I have giveaways. So. Good question askers. That's awesome. So if this flew by pretty quick and you have anything, so I think I went through this as well already. So recommendations. My personal recommendation is use asymmetric encryption. If you're not just encrypting your own data and reading your own data, giving somebody else a shared secret is a terrible idea. Who do you trust? I don't trust anybody, right? And you shouldn't. So, and this room is probably less trusting than most of the places I talk. So please consider using asymmetric key encryption. You'll be happy about it later. And then if you are moving data and you have large amounts of data or you need faster crypt, then you want to use AES, random AES keys and IDs for transfer using RSA to encrypt it. Please be sure to use cryptographically secure random number generators, right? The rand function on most development languages is not cryptographically secure. It is pseudo-random, and all pseudo-randomness is, who knows what pseudo-randomness is? All right. So pseudo-randomness means that I have a defined list of values, and I'm going to go through them in order, but where I start, nobody knows. Unless you're using a time-based generator, which ran on most operating systems and on most development languages, is going to use time. So you can actually guess where it's going to start based on what time it is. You don't want to use that. What you want to use something that's using either a random generator that's physical, or on Linux, you want to use dev random. Dev random uses all kind of machine fuzzery as far as like what's the current speed of the CPU, what's the temperature of the CPU. It uses all the information it can gather from the machine itself, which is individual to that machine, to try and add more entropy into determining where it's going to start on a random list. So make sure that your pseudo-random generators are cryptographically secure. That's super important. When you're generating IVs, when you're generating keys, all that type of stuff, it's super, super important to make sure you're using the right random. And then use bcrypt, scrypt, and R.2i for passwords. Don't use hashing. Don't use PPKF2 if you can avoid it. Strengths, the minimum is AES 256 CVC. Depending on your machine, and you'll probably be able to find this if you do a quick Google for your processor family and AES. It'll tell you if 512 is faster than 256 because on some machines, because of the way that they're built internally, AES 512 is actually faster than AES 256. And make sure that when you're doing your HMAC that you do a SHA-256. RSA, like we talked about, was 2048 minimum. Really want to use a 49.6 key. Really do. But you can get away with a 2048 currently. And make sure that you use PKCS1 OAAP padding. Do not use PKCS V1 V15. It is not cryptographically secure. And then make sure you're using an RSA SHA-256 hash for your password, and hash until it hurts, hash until it hurts, hash until it hurts. Really. You owe it to everyone out there and yourselves to make sure that people hash until it hurts. Because I don't think twice when it takes a half a second for a web page to load. I really don't. If all that time is doing hashing, then I'm in good hands. So that's all I have. If anybody has any more questions.
Yeah, my company, my organization's migrating from SHA-1 to SHA-2 currently. The system engineers are responsible for that build. I was very glad it didn't go into the cybersecurity people because I didn't know what I was doing with that. But could you explain what the difference is between SHA-1? Is that just for password protection?
I gotta hope not. SHA should never be used for password protection. So what the difference between SHA-1 and SHA-2 which is actually the 128-bit, 256-bit hash, is that your hash size is twice the size. So instead of being 128 bits, it is 256 bits, which means you're going to have fewer collisions. So if you're trying to sign data or determine that one large file is the same as another one, or one piece of data is the same as another one, you can hash those to figure that out for a fingerprint. But if you're using it for passwords, you're still a mess. I promise you, you're still a mess. There are people in this room that can crack every password that you've got in a matter of minutes. I promise you. And it's a scary thing, because there are a lot of companies that are in exactly the same situation where it's, they're using SHA passwords. Because at one time, it was considered okay, but that was a while ago. So you should ask those people what they want to move from SHA-1 to SHA-2 for, and make sure it's not passwords. You want them to use decrypt or scrypt. Any other questions? Okay, so I'm 4 minutes left early. So then you get a Staples thing. So they're giving out prizes for stuff. So who else asked a question? Because I remember you asked a question. Anybody else asked a question that I forgot? I saw something you didn't. I'll get over to something.
Do you have any recommended
I
books?
don't think I'm gonna make it to catch a lot.
Study book photography.
Books on cryptography. I mean, honestly, I don't. I'm not a cryptographer. But if you're looking to get in depth,
HD.
I check out Wikipedia. It is ridiculously. There's so much on it. I mean, I guess it's a data store built by engineers, right? So there's a ton of information on cryptography, pictures and equations. If you want to get back onto like one of these nice learning sites and try and figure out your math again, because that's what I had to do. It's like I took differential equations, but I don't remember this crap. So I had to actually go take a course to remind myself how to read the computations. But yeah, I would check out Wikipedia. Just start with whichever encryption you want to look into, and it will kind of get into it.
Okay.
You can look at Bruce Schneider's Applied Crypto.
That one does sound familiar.
Hacking Narda exploitation also has like a primer on how to start developing.
Awesome. Any other questions? Yeah.
Any particular libraries you recommend?
So what I particularly recommend is something that's going to be regularly updated and is reviewed by the people in this room. So popular libraries like OpenSSL, although it has had its problems in the last 2 years, is at least vetted. There are, Python seems to be popular here, and I do Python professionally for a living. And there are I'd say at least 10 different cryptography libraries that do their own crypto, and I would say no. Like I said, OpenSSL has its problems, but when the problem's found, the problem's patched immediately, and it's sent out, so you're probably safe using that. I know in PHP, they're actually getting rid of mtcrypt and just using OpenSSL. In Java and Android development, there's Bouncy Castle and Spongy Castle. Those are actually, they have a version of Bouncy Castle that is now FIPS compliant, for those of you who know what FIPS compliant is. And I don't know the .NET world, to be perfectly honest. I don't. I actually have to do .NET 12, but I have no idea how to do it. And actually, if you use, for Node.js, it uses OpenSSL. So just use it's actually built into the standard library for crypto stuff. You'd have to get, for password hashing, they only offer PBKF2. But you can, there's plenty of libraries out there for, and good libraries out there for bcrypt and scrypt. Any other questions? Cool, well, I appreciate you coming and listening to me ramble on about crypto.